Swayam Prabha. Digital India. Educated India.
Dear students, I welcome you again on the 12th lecture on Mineralogy course offered by the Department of Geology and Geophysics, IIT Kharagpur. This will be also the third lecture under Optical Mineralogy, which we have introduced in the previous two lectures here. Now, let us see what we will study in this lecture today. Here I will introduce to you the concept of optical indicatrix and optic orientations of a mineral, and I will tell you about the indicatrix of isotropic mineral, uniaxial mineral group and biaxial mineral group here. I will also define to you the extinction and extinction angle. I will define them. I will also tell you the significance of these values and how this extinction angle measurement is dependent on optic orientation here. Now, what is an optical indicatrix? Optical indicatrix is a three-dimensional graphical representation of the changing refractive index of a mineral. And I will show you with diagrammatic sketches what is a three-dimensional representation of each mineral where the distance from the center to the indicatrix surface is essentially the refractive index values here. The shape of the indicatrix has three broad varieties. One is a sphere, one is a biaxial ellipsoid, and the third is a triaxial ellipsoid. And I will show you the shape of an indicatrix is a function of the crystal's optical class. That means, whether it belongs to isotropic mineral group, uniaxial mineral group and biaxial mineral group. And it is also the first order function of the crystal system to which the mineral belongs. And here the measurement of refractive index is done as the distance from the center to the point on the surface of the indicatrix, and this is the value of the refractive index at that point. So, immediately we will be able to understand that this value of refractive index changes at different directions here. So, this is also a directional property of a mineral in terms of a three-dimensional geometry, which we call it as optical indicatrix here. Now, let us start with optical indicatrix of minerals belonging to the isometric crystal system here. So, let us recapitulate what is an isometric crystal system and what is the crystallographic axis in an isometric crystal system. So, in isometric crystal system, this is understood, the unit cell of it is a cube and all the dimensions are equal A and A. And if you see a representative mineral of an isometric crystal system is a garnet, and here this garnet, a dodecahedron shaped garnet is shown here, and all the three axes A1, A2 and A3 axis are shown, and an indicatrix is indicated in this particular mineral here. So, for an isometric mineral, the indicatrix is a sphere where the refractive index, that is n, is constant in every direction, and every optic orientation, if you cut this sphere and that passes through the center, it will be a circle. We call it as a circular section of the indicatrix. So, just like this is the circular section of the indicatrix here, and what is important here is that the radius of the circle is the refractive index here. Now, what is important here, because this is a circle, the birefringence is 0, and what is the significance of birefringence is 0? Immediately you know that the retardation and path difference is a multiplication of birefringence of the mineral and the thickness of the mineral. So, since the birefringence is 0, the retardation is 0. What is the other implication of this is that a set of rays or waves, when they vibrate in the circular section, there is no double refraction. So, and the mineral, because tau is equal to 0, retardation is equal to 0, the intensity of light that will pass through the analyzer, that value will be 0, and it will remain as dark. That will be, it is under extinction position under all optical orientation. And that's the reason the minerals which crystallize in the isometric crystal system, they have an indicatrix shape which is sphere, and these minerals are called isotropic minerals here. And this is a very good example of the same garnet, natural garnet crystal here. You see, the shape is just like of a equidimensional in all directions here. So, that is the essential feature of minerals belonging to the isometric crystal system here. The other important aspect is that you can understand here, if all the sections which passes through this sphere, but the center of the sphere, if it is circle, then you can immediately imagine that there are innumerable circular section of the indicatrix that is possible here. So, all optic orientation, whatever the direction you cut this sphere, this will be circle. And if you draw a perpendicular to this circle, you will define shortly the direction will be the optic axis of the mineral. So, at this stage I will just try to make a comment here that in case of isotropic mineral groups, there are infinite numbers of optic axis, and that is an important property of isotropic mineral group here. Let us show you that particular importance here, that what is the significance of the circular section of the indicatrix for a mineral belonging to the isometric crystal system. Here there are two photographs shown here. The photograph to the left shows garnet seen under plain polarized light, and these are the crystals of garnet here, and this is very high relief, and this color is pale pink to colorless here. And when the same mineral is seen under cross polarized light, you will see that everywhere the mineral is dark or under extinction position. This is the characteristic feature of minerals belonging to the isometric crystal system, or the characteristic of isotropic minerals here. So, isotropic minerals, they will remain under extinction position under all stages of rotation of the microscope stage, and it emanates from that very important aspect here, that in circular section the birefringence value is 0, and that is the reason why the intensity of light that is resolved parallel to the analyzer vibration direction, that value is 0. So, 0 transmission of light passes through the analyzer, and that is the reason why the mineral will be dark or under extinction position, and this will be the characteristic feature of isotropic mineral group. Let us now come to anisotropic mineral groups here, and let us consider a type of anisotropic mineral group which we call it as uniaxial. Now, immediately you understand what the uniaxial term means. Uni means one, and axis in this particular case is an optic axis. So, there is only one optic axis. So, we will define why there is one optic axis, and we will also define what is an optic axis here. Before that, let us consider that this fundamental aspect, that what will be the indicatrix of a uniaxial mineral group. The uniaxial mineral group, they have an indicatrix which is a biaxial ellipsoid here. In 3 dimension, this is an ellipsoid, and there are 2 axes here, one corresponding to extraordinary ray vibration direction and the other corresponding to ordinary ray vibration direction here. Most importantly, these uniaxial minerals, they have a characteristic relationship with the crystal system here. They belong to the tetragonal, trigonal and hexagonal crystal system. Let us try to understand why this is so. What is the reason why minerals belonging to tetragonal, trigonal and hexagonal crystal system, they will come under uniaxial mineral group. So, this is a three dimensional orientation of a tetragonal mineral, and this is a three dimensional orientation of hexagonal and trigonal mineral group here. So, you remember in a tetragonal crystal system, the C crystallographic axis is vertical, and in a plane perpendicular to the C crystallographic axis, there are two crystallographic axes here. One is called A1 and the other is called A2. So, they are of unit, they are equal in length here, but they are unequal with C crystallographic axis here. What does it mean? That if you have a plane perpendicular to the C crystallographic axis, if the rays vibrate in that plane, the velocity will be the same everywhere here. So, immediately you can understand in that plane, the refractive index corresponding to the rays vibrating in that plane, we will have a unique feature of the optic orientation here, because the refractive index will be the same everywhere. You can consider that plane is a circular section of the indicatrix here, whereas the rays which will be vibrating parallel to the C crystallographic axis, that will be different, that velocity will be different compared to the rays which vibrate perpendicular to the C crystallographic axis or in the plane of the circular section of the indicatrix here. So, the ray which is which vibrates parallel to the C crystallographic axis, and the C crystallographic axis is a unique direction here, and that direction we define it as an optic axis here. What does it mean? If any ray, a light ray propagates along the C crystallographic axis, then what will happen? There will be no double refraction. Why? Because the rays will all vibrate perpendicular to the C crystallographic axis, that will be in the plane where you have A1 and A2 crystallographic axis there. So, essentially that will be a circular section of the indicatrix where the refractive index will be the same here. So, what happens here? Because in minerals belonging to the tetragonal and hexagonal crystal system, you have the same feature, that you have one C crystallographic axis, and in the perpendicular to the C crystallographic axis, that is with the horizontal plane. In tetragonal system, you have A1 and A2 axis, and in hexagonal crystal system in A1, A2 and A3, they are all equal in length. So, essentially in this horizontal plane, the rays vibrating in this horizontal plane, they have equal velocity and they have the same refractive index, and there will be a circle here. So, this particular unique feature of minerals belonging to tetragonal, hexagonal and trigonal crystal system, they have one C crystallographic axis, and that is your optic axis here, and this will be parallel to the C crystallographic axis, and that is also be the axis which is 4-fold axisymmetry, 3-fold axisymmetry or 6-fold axisymmetry here. Now, let us see what is the three dimensional orientation of the optical indicatrix of a uniaxial mineral here. This is one, as I told you here, this is a biaxial ellipsoid here. Now, if you have a section here which contains this C crystallographic axis, which is your optic axis. So, let us now define the two rays that are present, that after double refraction they vibrate parallel to the C crystallographic axis, which is your optic axis. That ray is called extraordinary ray, and the refractive index corresponding to this extraordinary ray is called epsilon, or if sometimes it is also written as Ne, refractive index corresponding to the extraordinary ray. Whereas, the ray which vibrates in the plane perpendicular to the optic axis, that is in the circular section of the indicatrix, those rays are called ordinary ray. And remember, the ordinary ray, they behave Snell's law, extraordinary ray does not behave or does not obey Snell's law here. Now, the other important issue here is that if you have an optic orientation here, where you have the C crystallographic axis, so or the optic axis, then you have an optic orientation which will be an ellipse here, and you will have a semi major axis. In this particular case, I will define you shortly. In this case, the semi major axis is the refractive index corresponding to the extraordinary ray, and in this case the semi minor axis here is the refractive index corresponding to the ordinary ray. Very often we call it as omega, and this one we call it at epsilon. In this particular case, epsilon is greater than omega here. When in uniaxial mineral any value or epsilon value is greater than n omega or refractive index corresponding to the ordinary ray, we call those uniaxial minerals has an positive optic sign here, and the shape of this kind of biaxial ellipsoid we call it as prolet type or rugby ball type here. The converse. So, what is the other important issue here? When you have n epsilon greater than n omega, where the velocity of extraordinary ray is lower than that of the velocity of the ordinary ray. That means, extraordinary ray is the slower ray, only then you have epsilon greater than omega, and in that situation uniaxial minerals optical indicatrix is called prolet. Now, if you have a different situation here, where you have a shape which is the shape of an oblate shape here, where n epsilon is less than n omega. So, our refractive index corresponding to the extraordinary ray is lower than the refractive index corresponding to the ordinary ray. So, this is the situation here. So, then we call it the uniaxial mineral has a negative optic sign here. So, that is a very important aspect here, that this positive and negative optic sign in uniaxial mineral is essentially due to the velocity differences between extraordinary and ordinary ray. In case of uniaxial negative mineral, E ray is faster, E ray is the faster ray than the O ray here. Now, I would like to define two important aspects here with respect to the uniaxial indicatrix. Now, the optic orientation which contains the C crystallographic axis or optic axis here, which will be essentially the an elliptical shape here. That kind of optic orientation is called principal section of the indicatrix here. So, in the principal section of the indicatrix, as I will further define it here, where you have the true value of epsilon and the value of omega here, and the birefringence will be maximum here. Whereas, in the circular section of the indicatrix, which will be only 1, there the birefringence is 0, and importantly, as we have seen in case of isotropic mineral group, here also the uniaxial mineral and an anisotropic mineral will behave just as an isotropic mineral if the optic orientation is the circular section of the indicatrix, or optic orientation is perpendicular to the optic axis. In that situation, a uniaxial mineral will just behave just like an isotropic mineral here. Now, this I will try to further define here with respect to different images here. Now, you see here, this is the biaxial ellipsoid of which is an indicatrix of an uniaxial mineral here. Now, what you can do here is that you can cut this indicatrix in different ways, and let us consider that there are 3 different optic orientations here. Let us consider this optic orientation. Here you have the C crystallographic axis, which is also the optic axis here, and you have also this direction here, which is your gamma. So, you have epsilon and you have gamma here. So, that kind of optic orientation which is parallel to the optic axis is an ellipse, and you have the true value of epsilon and the value of omega, and this kind of optic orientation is called the principal section of the indicatrix. And here the birefringence is, this symbol is shown here, this is the maximum value here. So, this is essentially shown here, this is the principal section of the indicatrix. In this case, the optic axis is shown to be horizontal here, and in this plane you have the true value of the epsilon, and you have the omega which will be an ellipse, and you have the maximum birefringence here. And I have told you previously, the order of interference color is dependent on the birefringence value here, and this is the optic orientation, that is in the principal section of the indicatrix. You have the maximum birefringence. So, this will be the optic orientation which will be suitable for determination of the true order of interference color of an anisotropic mineral, in this case an uniaxial mineral here. Now, this is another optic orientation which is perpendicular to the optic axis, which is the circular section of the indicatrix, which we have already defined. Here this optic axis is vertical, and this is the plane of observation, is the circle here. So, in this case birefringence is 0. So, the radius is n omega or omega. So, this will be it will be completely dark under cross polarized light, and it will behave as an isotropic mineral here. And if you have a random section here, in that random section it will still be an ellipse, but important thing that the semi major axis will be a value intermediate between true epsilon value and omega value here. We call it as epsilon dash, and the birefringence here, that is epsilon dash minus omega, will be a value which will be lower than the true birefringence value here. So, that is why this is a value which is between 0 and maximum value here. So, in those optic orientation, the order of interference color will be lower than the true order of interference color of a uniaxial mineral here. So, this is, I am trying to reinforce here the importance of the optic orientation. The same mineral, how it is cut, how its optic orientation is there, and its optical behavior will be different from its different grains of the same crystal because of its different optic orientation here. And I think that I have been able to tell you here the significance of the two terms here, the principal section of the indicatrix, circular section of the indicatrix, and random section here. So, with respect to the uniaxial mineral, I think that I have been able to emphasize upon these terms here. Now, let us come to another mineral group called biaxial mineral group. So, as you see here, the biaxial mineral group, the terminology tells us that there are two axes here. So, immediately we will know that there are two optic axes here. In case of uniaxial mineral, one optic axis. In this biaxial mineral, there are two optic axes here. Now, the indicatrix shape here is triaxial ellipsoid, and the refractive index n is different and in different directions here. And the minerals belonging to triclinic, monoclinic and orthorhombic crystal system, they come under the biaxial mineral group. And there is a reason behind this, because in all the three crystal system, there are three crystallographic axes here, that is A, B and C, and A is not equal to B, is not equal to C. So, obviously, because of this anisotropic behavior, that is the velocity of light will be different in different planes containing A and B, C crystallographic axis. So, that is the reason here that you have, instead of two vibrations in uniaxial minerals, there are three vibrations here. Amongst these three vibration direction, which you call it as x vibration, y vibration and z vibration, x is the fastest, z is the slowest and y is intermediate. And the refractive index corresponding to x, we call it as alpha, and the refractive index corresponding to y we call it as beta, and the refractive index corresponding to z we call it as gamma. Now, immediately you know gamma is has the maximum value here, where alpha is the lowest value here, and beta is intermediate between alpha and gamma. So, the principal section of the indicatrix obviously will be the one where you have the maximum birefringence, that means gamma minus alpha, that will be the highest value here. And if you have to have gamma and alpha, that means you have to have x vibration and z vibration to be present in that section. So, this will be the xz section here. So, maximum birefringence, that will be the gamma minus alpha value here. And I also tell you that since there are two optic axes here. So, you have two circular section of the indicatrix, and the radius of those circular section of the indicatrix will be beta, and I will show you shortly how this is so. Now, this is the three crystals that has been shown here with respect to orthorhombic, monoclinic and triclinic crystal system, and you see that there are three optical indicatrix has been shown here. These are triaxial ellipsoid here. Now, in this diagram below, what I have tried to do here is that I have cut this indicatrix into three planar orientations here. One, which is the xz section here, where this is the z vibration direction, and this is the x vibration direction here. So, that optic orientation is an ellipse here, and the refractive index corresponding to z is gamma, and the refractive index corresponding to x, this is alpha here. So, this is the xz section here, and gamma minus alpha is the maximum value here. You can also have a section which is perpendicular to xz, this is the yz section here. So, what you have here, the refractive index corresponding to z, that is gamma, and the refractive index corresponding to y is beta. So, you have the gamma minus beta, it is still an ellipse, and gamma minus beta will be lower than gamma minus alpha. Whereas, you can think of another orthogonal orientation here, that is the xy plane, where you have the two vibrations x and y, and their corresponding refractive index, that is with respect to x, this is alpha, and with respect to y, that is beta. So, and this is the beta minus alpha. So, this is the lowest value amongst these three here. Now, let us move forward and try to see further about the different issues of the optical indicatrix here. Now, you see here, this is a triaxial ellipsoid here, and you can see these three planes as I was telling you here. This is this plane here, this is your xz plane, this plane here, this is your yz plane here, this is your y, and this plane here, this is this particular plane here, this is your xy plane, where you will have y vibration direction, and this is your x vibration direction here. One of the most important aspects of this biaxial mineral is the existence of two optic axes here. Now, why this is so here? Now, try to see this. This is the principal section of the indicatrix of biaxial mineral here, where you have the two optic axes that are present here, which is this axis and this axis here. Now, let us try to understand this particular issue here. This is an ellipse, this is the semi major axis, this is the semi minor axis. So, this value is gamma and this value is alpha. Now, if you go from this point here and progressively come to this point here, and everywhere on the periphery, if you join from the center to this point in the periphery, that will be your refractive index here. So, what will happen here is that as you come progressively from this point to this point here, where gamma is finally converted into alpha, you will be having one point here, where the distance from the center to this point will be intermediate between gamma and alpha, that will be your beta value here. So, you have one beta value here. So, this is the point where on either side of this z vibration direction, in this direction and also in this direction you can find out here. Now, these two directions is your beta direction here. So, what you can do here is that you can draw a circle with beta as the radius, as you have done here. So, you have a circle here and you can draw another circle here, this circle here. So, these two circles they intersect along this line, that is your y vibration direction here. And because this is the circular section of the indicatrix, you can draw a perpendicular to the circular section. This perpendicular is called optic axis with respect to this circular section, and with respect to this circular section you can draw another perpendicular to it, that is this optic axis here. So, you have two circular section of the indicatrix and there are two optic axes. This is the reason that you can tell that why minerals belonging to triclinic, monoclinic and orthorhombic crystal system have two optic axes here. Once you know that there are two optic axes here, now there are two important properties that come out here. One of these is the angle between the two optic axes here. This angle is called optic axial angle, called 2V. Now, this angle can be an acute angle or can be an obtuse angle here. When the angle is acute and the bisector of this acute angle, we call it as acute bisectrix, and if it is defined by the z vibration direction, then we call that the biaxial mineral has a positive optic sign here. And in that situation, when Z is the acute bisectrix, that is called BXA, A is the acute, this is the acute bisectrix, that is biaxial positive, and in that situation this beta value is very close to the alpha value here, that is beta is closer to alpha. But when the acute angle is bisected by the x vibration direction, that means x is the BXA, then we call this as biaxial negative value here, and in that situation beta, this value is closer to gamma here. Now, depending on the value of 2V, when 2V is equal to 0, then you have only one optic axis and that is uniaxial, and for biaxial the 2V value will be between 0 and 90 degree. When 2V is equal to 90 degree, we call this as optically neutral here. And this is the same thing, that how you cut this particular biaxial ellipsoid in different directions of light vibration, we call it 1, 2, 3, 4, 5. There are different directions of vibration. When one is the direction of propagation is along z, and so when the direction of propagation is, say for example, along x, and then you can cut this particular section and intersect with the triaxial ellipsoid, you can have ellipse of different shape, and in some cases when you are at 3, so where you will have the circular section of the indicatrix here. So, one important aspect here is that in case of biaxial indicatrix here, there are different possibilities of optic orientation and you have different birefringence possible here. But the two birefringence of a biaxial mineral is only be seen in the principal section of indicatrix of this mineral. What is the principal section of the indicatrix? Where you will have the two optic axis will be there. That is essentially is your xz plane of the indicatrix here. That is also called the optic axial plane, and the direction which is perpendicular to the optic axial plane, we call it as optic normal, that is your y vibration direction here. Okay. Now, let us now classify the minerals on the basis of isotropic and anisotropic group here. So, isotropic mineral groups, there are certain examples you can see, that garnet, diamond, fluorite, spinel, they are good examples of isotropic mineral group here, whereas anisotropic mineral groups can be classified into uniaxial and biaxial. So, uniaxial minerals with positive optic sign, the best example is quartz, which we always use, along with other uniaxial positive minerals, the examples are zircon and rutile, the best example, and there are other examples mentioned here. And uniaxial negative minerals, they are apatite. The best example we always mention, that is calcite, and you have beryl, tourmaline and corundum. And you can also note another very important uniaxial negative mineral, we call it as capolite, which is a mixed silicate carbonate group of mineral here. And in the biaxial group, you have the positive minerals are magnesium N member orthopyroxene, we call it N-statite. You have clinopyroxide like diopside, sillimanite, and you have plagioclase of certain composition, particularly from the sodic N member. And the biaxial negative mineral group, these are potash sulfur is always biaxial negative, as also muscovite, hornblende, and also plagioclase of certain compositions, they are also biaxial negative here. Okay. Now, this is the one that I discussed in a previous class here, the significance of the optic orientation in terms of the order of interference color here. So, I just very rapidly pass through this here. So, these are the 4 images of a crystal of olivine here, the magnesium rich olivine here. You see they have different order of interference color. The color is different and the order is also different. And I discussed in the last class that of this all different mineral grains, this mineral grain showing yellow green second order interference color, that is the highest order here. And immediately I told you that this will be the principal section of the indicatrix of the mineral corresponding to that composition here. And I told you how the second order interference color can be used, and knowing this thickness of the mineral, you will be able to calculate the birefringence value using the Rice-Sorensen color chart here. So, important that the different order of interference color of a mineral is essentially an optic orientation of the crystal here. Circular section of the indicatrix will show the lowest order interference color and will behave as an isotropic mineral, whereas the principal section of the indicatrix will give rise to the highest order of interference color, and random sections will give an order of interference color which will be lower than the true order of interference color here. Now, the next property that we will learn now is called extinction angle, and this is also the property that is to be studied under cross polarized light. What is an extinction angle? This is the angle between a crystallographic axis and the vibration direction of a mineral here. And the crystallographic axis is essentially defined by the morphological direction of the crystal, the long orientation, or if the cleavages are present here, the cleavages are essentially parallel to the crystallographic axis, they will define this as an indicator of a crystallographic axis. There are 3 types of extinction we know about. When the extinction angle is 0, we call this as parallel or straight extinction. When the extinction angle has a non-zero value here, we call it as an inclined extinction. And when the vibration direction bisect the angles between 2 equivalent morphological reference direction or 2 equivalent cleavage directions or 2 equivalent crystallographic axis direction here, and that is essentially that bisector, that is makes 2 angles here which are equal here. That kind of extinction we call it as symmetrical extinction here. Now, this is a very nice table which summarizes the type of extinction that we see in minerals belonging to the 7 crystal system here. So, in minerals belonging to hexagonal, trigonal, tetragonal and orthorhombic crystal system, we see straight extinction here, and we also see symmetrical extinction in this hexagonal, trigonal and tetragonal crystal system, as well as in the orthorhombic crystal system and also in the monoclinic crystal system, where we see in orthorhombic we see straight extinction, monoclinic we see inclined extinction, but in certain optic orientation of monoclinic crystal I will show you that it also shows straight extinction here. And triclinic minerals will always show inclined extinction here. Now, let us see the basic principle behind this categorization of minerals showing straight extinction or inclined extinction here. So, in orthorhombic crystal system, you know that alpha is equal to beta is equal to gamma is equal to 90 degree, and the vibration direction x, y, z, they are of orthogonal orientation. Immediately you can understand that the crystallographic axis coincide with the vibration direction. So, that is why the angle is 0. So, you have straight extinction in minerals belonging to the orthorhombic crystal system. The same is true for tetragonal, trigonal and hexagonal crystal system, particularly in the principal section of the indicatrix. A angle C is 90 degree and E ray and O ray, their angle is also 90 degree. So, crystallographic axis coincide with the vibration directions, and they will also show straight extinction or parallel extinction. In case of monoclinic crystal system, alpha is equal to gamma is equal to 90 degree, but beta, that is the angle between A and C crystallographic axis, is not 90 degree. Here B axis coincides with the y vibration direction, and x and z vibrations, they lie in the AC plane here. In that plane, x angle z is 90 degree, but A angle C is not 90 degree. So, what happens? Z does not coincide with the C crystallographic axis. So, this in this optic orientation, which is the principal section of the indicatrix of monoclinic mineral, which is parallel to the 0 1 0 optic orientation, you have a value of z angle C, which is not 0, and this we measure as a measure of the inclined extinction or angle of extinction or extinction angle for a monoclinic mineral here. Whereas, in 100 optic orientation, I will show you that it shows straight extinction here. Whereas, in crystal system of the triclinic crystal system, the alpha is not equal to beta, is not equal to gamma, is not equal to 90 degree, and the crystallographic axis, they make an angle with the vibration direction. So, generally triclinic minerals will show inclined extinction. So, let us see with an orthorhombic crystal system here, and this I have already mentioned here, that alpha is equal to beta is equal to gamma is equal to 90 degree, and this is A, B and C orientation here. Now, let us consider there are two crystals of orthorhombic crystal system here. This system here, in this case, you see there is a cleavage here, and this cleavage is parallel to this 0 1 0 plane here. So, let us try to see here, this is the B crystallographic axis, this is the C crystallographic axis, and this is your A crystallographic axis here. And you see here this particular direction, that is your cleavage direction here. So, in sections, say for example, in 110 plane or say in 101 plane, what you have here, that this trace of cleavage, which is a vertical cleavage here, which is parallel to the C crystallographic axis. So, in this particular optic orientation, this cleavage direction will tell you, will be a marker of the C crystallographic axis here. So, everywhere if you draw an indicatrix position here or a particular orientation here, wherever you see, say for example, in 110 here. So, this is the direction, that is your C crystallographic axis, and also this is the Z vibration direction here, and this is the alpha dash vibration direction here. So, in this case what you have here is the crystallographic axis, that is C, coincides with the Z vibration direction. So, in this plane you have 0 extinction angle here, and you can also have a situation here in the 001 plane here. So, in this also case you have the trace of cleavage here. In this case, this will be a crystallographic axis, and here also it is, you have the two vibration direction here. This is the y vibration direction here, and this is the x vibration direction here. So, here also the vibration directions coincide with the crystallographic axis. So, immediately also in 001 plane you will also see straight extinction here. So, If you now go to another type of orthorhombic crystal where now there are two sets of cleavage here, and this cleavage system here is, say, let us consider this as 1 1 0 cleavage system here. So, this is this cleavage is of this orientation, another cleavage is of this orientation here. So, which is parallel to, say, 1 bar 1 0, and this is 1 1 0 plane here. So, what you see here, these cleavages are vertical, of vertical orientation here, and in this vertical orientation what you see here is that this vertical direction, there is a trace of the cleavage, say for example, in this plane. What is this plane here? This is your 0 1 0 plane here. This is your B crystallographic axis, which coincides with the x vibration direction here. So, this is your x vibration direction here. So, in this plane, the trace of this vertical cleavage is this line, which is parallel to the C crystallographic axis here, and in this direction, this is your z vibration direction, and this will be your y vibration direction here. So, this particular case, you see here the crystallographic axis and the vibration direction coincide. So, in 0 1 0 plane, the mineral will show straight extinction. Same you can also see in this plane as well. So, this is in 1 1 0 plane here, as I have discussed it with respect to this. Here also the crystallographic axis coincides with the vibration direction. So, in also in 1 1 0 optic orientation, it will show straight extinction. But what will happen in the 0 0 1 plane here? You see here in 0 0 1 plane, you have these two cleavage traces here, and what you have in these two cleavage traces. So, let us consider these two cleavage traces here, and there are two vibration direction. One vibration along this is your y vibration direction, and this vibration direction is your x vibration direction here. So, this is your y vibration direction, and this is your x vibration direction, and this morphological direction, that is the two cleavage traces, are bisected by these vibration directions here. So, this is what we call it as symmetrical extinction here. So, if you want to see symmetrical extinction here, you have to choose this 0 0 1 optic orientation, and you also can use this optic orientation as well. This is your 1 0 1 plane here. Here also you have see there are two sets of cleavages here, and this vibration direction, that is x, and this vibration direction which is bisecting, which both of these will bisect these two cleavage traces here. So, you will also see in 1 0 1 plane a symmetrical extinction here. Now, we can see this with respect to an orthopyroxene crystal here, a natural example of a orthopyroxene crystal which crystallizes in the orthorhombic crystal system here. Now, you see this is the optic orientation, you can see this is the 3 dimension here. So, what you see here, this is your B crystallographic axis, which is parallel to the x vibration direction. This is your C crystallographic axis, which is your parallel to the z vibration direction, and this is your y vibration direction, which is parallel to the A crystallographic axis here. So, they have two sets of cleavages here, as I have told you here, parallel to 1 1 0 and 1 bar 1 0. So, in 1 0 1 section here, you will be able to see the symmetrical extinction here, as also in 0 0 1 plane here. And this orthorhombic crystal system, the optic axial plane, or say for example, your principal section of the indicatrix is this particular plane here, which is parallel to 1 0 0 plane here. And what you have here, this plane here, 1 0 0 plane here, in this plane you have z and you have x. So, immediately in this plane, the x is parallel to B crystallographic axis, and in this plane you have z parallel to the C crystallographic axis. So, you will see straight extinction here, not only in the optic axial plane or the principal section of the indicatrix here 1 0 0, or also in the 0 1 0 plane here, or in optic normal plane here. Okay. So, let us now see with what happens in a monoclinic crystal system here. If you see in this monoclinic crystal here, So, this is the 3-dimensional orientation of the monoclinic mineral here, and you remember that this is the B crystallographic axis of a monoclinic mineral, and here it is parallel to the y vibration direction or the optic normal here. So, in that situation, this plane, which will be the principal section of the indicatrix here, which is parallel to 0 1 0. So, in this plane you will have z and you have x vibration direction as has been shown here. And what you have here in this case, this is also the optic axial plane. You have the two optic axes that has been shown here, and you also have the C and A crystallographic axis. So, in 0 1 0 plane or the principal section of the indicatrix, what you see here, the cleavage traces here, these are this cleavage traces here. There are two sets of cleavages. Let us for example, you consider there are two sets of cleavages are there, and the trace of that cleavage is this line here, which is parallel to the C crystallographic axis. So, these are the cleavage traces here, which is parallel to the C crystallographic axis, and this is this plane here. In this plane you will have x vibration and the perpendicular to the z vibration here. So, what happens here is the C makes an angle of A, which is not 90 degree. So, z and C crystallographic axis, they are not coincident, they make an angle, and this angle we call it as the extinction angle here. So, in the principal section of the indicatrix of a monoclinic mineral, that is in 0 1 0 plane, you will see the true value of the extinction angle here. Whereas, if you have this optic orientation is this 1 0 0 plane here. So, in 1 0 plane, this is the trace of the cleavage, which is the C crystallographic axis, which is parallel to the z here, and what you have here, you also have this vibration direction, that is y, which is parallel to B. So, here you see the crystallographic axis and the vibration directions, they coincide here. So, monoclinic mineral will show straight extinction in 1 0 0 optic orientation here, whereas in 0 0 1 optic orientation, this will show symmetrical extinction, as we have discussed previously with an orthorhombic crystal here. Now, this is the summary of the extinction angle that we see in different crystal systems here. So, these are the minerals belonging to the hexagonal, trigonal and tetragonal system. So, these are melilite, nepheline, apatite, corundum, zircon, we told you. So, they will generally show straight extinction, and if there are two sets of cleavages or there are two morphological directions, they may show symmetrical extinction in sections perpendicular to the C crystallographic axis or in 0 0 1 plane here. In orthorhombic minerals, as we told you, they will show generally straight extinction and may show symmetrical extinction in sections parallel to 0 0 1 or parallel to 1 0 1 optic orientation here. In monoclinic minerals, it can show straight extinction in 1 0 0 optic orientation. It will show symmetrical extinctions in optic orientations parallel to 0 0 1, and it will show true extinction, true inclined extinction in optic orientation parallel to say 0 1 0. And these are the minerals which shows inclined extinction. The minerals belonging to the monoclinic crystal system, they are clinopyroxene, clinoamphiboles, epidote and cyanidine here. And triclinic minerals, they will generally show inclined extinction here. And this is an example that I am showing you here, that how it shows inclined extinction, the two monoclinic minerals that I am showing here in with respect to clinopyroxene and clinoamphibole here. So, how we determine the extinction angle here? You take the 0 1 0 plane here, so which is your principal section of the indicatrix, which is the highest order of interference color of that mineral. You rotate the trace of the crystal face or cleavage parallel to the north south crosswise. This is the direction here, and you take the reading from the from this goniometer stage, and you take this value here. Now you rotate rotate this crystal in such a way, rotate the microscope stage such that the mineral comes to an extinction position here, where the vibration direction will be parallel to the north south crosswise, and you take the reading here, and the difference of this reading is your extinction angle here. And clinopyroxene shows a large variation of inclined extinction here. Generally, it is of the order of around 40 degrees, 40 to 50 degrees, but it can also, for some species of clinopyroxene, it can exceed here. And same way, clinoamphiboles also have the same extinction angle, but generally the clinoamphiboles, the extinction angle is the order of 10s to 20s in this value, which is much lower than that of clinopyroxene. Now, I will use this knowledge of the measurement of extinction angle in plagioclase to determine the anorthite content here. To do that, what you have to do here, you have to have an optic orientation of plagioclase, which is perpendicular to the 100 orientation here. So, in this section there will be the 010 interfaces will be parallel to the llI twin here. So, these planes are the traces of the 010 interface, these are the llI twin here. I will discuss this in a later section, and you will also have 001 cleavage traces here, these lines here, and the angle is of very close to 90 degrees, actual angle is 86 degree. Now, rotation of the trace of the 010 plane into north south orientation. So, you rotate it and the twin plane is parallel to the north south orientation, and the reading of the angle value from the vernier of the microscope stage, you get this value here, and you rotate the vibration direction x dash. So, these are essentially the x dash vibration direction here. So, you rotate it parallel to the north south vibration direction, and you get the another value value 2 from the vernier, and the extinction angle will be the difference between the two here. And what you see here, so this has been this extinction angle with respect to the plagioclase composition has been calibrated with this curve here, both for plutonic and metamorphic plagioclase or in volcanic plagioclase here. Particularly, if this is from this plagioclase, this is from plutonic igneous rock or metamorphic rocks here. In this case, the extinction angle is measured as 31 degree. So, you can from the 31 degree, you can put it here and see where you are on this curve. At this point here, you can see the plagioclase composition here. So, from left to right, the anorthite content in plagioclase progressively increases here, and here that value comes out at say anorthite 57 here. So, this is the way you can use the extinction angle in plagioclase to know its chemical composition here. So, in nutshell then I summarize that we can use the optical indicatrix and to identify three classes of minerals, isotropic, uniaxial and biaxial minerals, and how the indicatrix can give us an idea that under different optic orientation there will be different optical properties, particularly in relation to the birefringence values here. And I also have defined the concept of extinction angle and the different types of extinction that is possible in minerals here, and with different examples and how to measure it, this extinction angle I have defined it here. Hope this will be useful for you when you will be doing the hands on training with microscope. Thank you.